say that. Great. It's my great pleasure to introduce Yong-Hin Noi. Yong-Hin is a senior PhD student at Stanford University, working with David Xie. In my opinion, Yong-Hin's group is one of the best in the blockchain space with a particular focus on consensus security. I guess you will understand what is consensus security after his talk. So whenever Yong-Hin has a new paper, I will read it. And I know many others are doing the same thing. Welcome, Yong-Hin. Thanks for joining us today.
Thank you so much for having me. Thank you so much for the kind introduction. It's really great to be here. Thank you all for being here. And I will give you over the next about 50 minutes some overview of the work that I have done together with my advisor David and some colleagues on Ethereum security. So the clickbaity title that got all of you here is Ethereum after the merge, is it still secure? And the merge, as you all know, happened in September of this year. Ethereum switched from proof of work to a proof of stake protocol. And we've been doing in the months and years leading up to it, we've been doing some security analysis on this protocol, and that's what I'm going to talk about in the next about 50 minutes or so. If you have any questions, post them on the chat, and I'll try to answer them as I go along, or just ask them, unmute yourself and ask them, and otherwise we can discuss them after the talk. So I've already said, this is joint work with my advisor, David, with my colleague, Nusret, and with a collaborator from the Ethereum Foundation, Francesco. And in order to understand this question, Ethereum after the merge, is it still secure? We need to, track a little back and go a little more high level and understand, what is Ethereum and what are other blockchains trying to do? And what does it mean for this for a protocol like this to be secure? So blockchains are an instance, a way of solving what we call the consensus problem. The consensus problem, in the consensus problem, you have a bunch of clients like Alice and Bob, and you have a consensus protocol being run by a bunch of nodes. You can, maybe they are miners or validators. We call them in the Ethereum context. These are, the computers here, and the job is as follows. Alice and Bob issue transactions, and these transactions arrive at the validators in no particular order, right? Because why would they be ordered, right? So some see Alice's transactions first, some see Bob's transactions first. In order to execute these transactions in a consistent way, these nodes input the transactions into a protocol, they talk to each other, and they come up with an ordering of these transactions. So you can think of a consensus protocol, in a very abstract way as kind of a box that takes in transactions in no particular order and outputs a ledger. Every node outputs a local ledger, an ordering of these transactions. There's a problem, old problem that goes back to the 1980s. And in order for a consensus protocol to make sense and to be useful, we wanted to satisfy at least two properties. One is called safety, which means that these ledgers that are output by different honest nodes at different points in time, they better be consistent with one another. You can think of this as, bad things don't happen, bad things being inconsistency across honest nodes. And the other property is liveness, which you can think of as transactions should make it to the ledger soon, right? Or more informally, you can think of this as good things do happen in this protocol, right? So with these two properties, exactly good things happen. Good things happen and bad things don't happen. And it's really important that you have both of these properties, right? So a safe protocol without the liveness properties is easy to get, right? Just output an empty ledger, then you're always consistent. It's not very useful though. And a live protocol without safety is also very easy to get because, just output the transactions in whatever order you receive them, right? Then you're not consistent with your peers, but hey, it's live, right? So it's really important. Both of these properties need to come together to have a secure consensus protocol and to use the protocol for something that we then call state machine replication, right? So once we agree on a ledger, we can then, every node can then go through the sequence of transactions and execute them in a deterministic state machine, and then they will all reach the same states. So this means that, Alice gets, for example, her transactions are confirmed, and Bob's transaction is rejected, and this happens in a consistent way across all honest nodes. So why is this problem hard? The problem is hard because the communication network and the environment that these nodes operate in is not ideal, right? In particular, some of these nodes might not be following the protocol. They might be malicious. They do whatever they can in order to deviate in whatever way possible to try and disturb your consensus protocol. Whenever nodes talk to each other, there might be a delay. Sometimes, maybe the delay is subject to a known upper bound delta. Sometimes even that upper bound might be violated. Right? So there might be something that we call a network partition. And finally, these nodes, you're not guaranteed that they're always there, right? Sometimes they're very sleepy. Sometimes they just go to sleep and they wake up like a week later. So this is also something you have to deal with. And the methodology here really is, usually we try to come up with a model to describe all of these imperfections of the environment that the protocol operates in. And then given, the description of the space of all adversarial strategies, we want to have a proof that the particular consensus protocol that we have in mind satisfies safety and liveness. So we can exercise this, way of thinking about the problem now and go back to good old proof of work Ethereum, right? The protocol that Ethereum was running basically before the merge was a proof of work protocol, and it was very similar to Satoshi Nakamoto's longest chain protocol. Right, so okay, I told you, let's exercise this a little bit. I told you a consensus protocol is this thing that takes transactions, right? And then it's a box. So what's in this box for proof of work Ethereum? It's basically, it's a very simple protocol. It's a big forever loop. And then there are 4 steps in the loop. The first step is, prepare a new block extending the longest chain with a bunch of unconfirmed transactions. The second step is try to solve this hash puzzle that constitutes proof of work. And then if you're successful, then you broadcast this new block, right? Now you have a valid block because it has valid proof of work, and you broadcast this block, and everybody adds this to their local tree of valid blocks. And then in the tree of valid blocks that every node has, right, you identify first the longest chain, and then on the longest chain, you chop the last k blocks off. Okay, this is what in Bitcoin we call like k blocks deep, right? K in Bitcoin, common wisdom is to pick k equals 6. But yeah, this is just to remind you of what's happening. And then, whatever is left in the longest chain after you chop k deep blocks off is what you output as the ledger. Okay, so these transactions in that sequence, that is what you consider confirmed, and that's what you're gonna execute. And this is what your state is. This is what the blockchain has confirmed. Okay, so our method is, right, model and then proof. And then for Nakamoto consensus, both in proof of work, but also in proof of stake, we get theorems like this. Assuming a bounded network delay with dynamic participation, so meaning that nodes can go to sleep, right, and they can wake up later. And assuming an honest majority among the ones that are awake, Nakamoto consensus is secure. So that's good. Okay. So this proof of work Ethereum before the merge. How about the protocol after the merge? So here it is. Okay, so this is an illustration of on a very, very high level the proof of stake Ethereum protocol as it's running today. If you want to read up on this, there's an archive preprint called Combining Ghost and Casper. And you already see, oh, this is kind of complicated, right? This looks much more complicated than these 4 steps that we had in the proof of work protocol. In particular, this big box now is internally made up from 2 constituent protocols, right? It seems like the big protocol, the big box, contains smaller boxes. There are consensus protocols within the big consensus protocol. That's perhaps the first thing you notice. The second thing you notice probably, hey, wait a minute, this seems to be violating what I told you before, because there are two outputs here. There is a chain tip output and there's a finalized chain output. What does that mean? I told you earlier, consensus protocol is a thing that takes, transactions in, ledger out. Now it takes transactions in, but two ledgers out. What does that mean? How does that make sense? And so this is what we're try to shed some light on in the coming minutes. So then we can ask, our standard questions we've been trained on. What's the model? What's the proof for this protocol, right? And the problem is, at the time, there was no model of, what can the adversary do in this protocol, and there was no proof of security properties that this protocol would satisfy. In particular, the lack of a proof doesn't necessarily mean it's insecure, right? But this protocol has a bit of a history of things breaking, and there are two aspects that I'll talk about more in this talk. One is about this feedback loop, right, between the two protocols, LMD Ghost and Casper FFG, right? You see that, if you took a control theory class once, you'll have grown careful around, feedback loops in block diagrams, right? Those need careful analysis, and the same is the case here. So this feedback loop, turned out to be rather brittle. So there was an attack in 2019 called the bouncing attack. There are other attacks that still have to do with this interaction between the two subprotocols. There are some ideas on how to mitigate those, but I think it's fair to say that this interaction, has been rather brittle in the past. And the other aspect is specifically about this first subprotocol. Okay, so there are two protocols here, LMD Ghost and Casper FFG. We'll talk about more. We'll talk later more about what properties they have and why it's these two protocols and how they are composed and stuff. But LMD Ghost is also rather brittle. And on an even more general level, right? There's no confirmation rule and there are no security guarantees for LMD Ghost, at least not at the time. And we showed an attack on LMD Ghost called the balancing attack in the fall of 2020. That attack needed adversarial network delay, which people thought was a bit generous of an assumption to give the adversary. So we later showed that this attack can even be pulled off without adversarial network delay. In response, there was a patch to the protocol trying to make this attack go away. We then showed that there's another provision in the protocol with which you can basically launch the same attack again, for which there was then another patch applied to the protocol. And this is pretty much where we're at. So somehow, the security analysis of this protocol has turned into a bit more of a game of whack-a-mole than we're comfortable with. And the question is why, right? I told you that this has been studied in computer science. This problem of consensus has been studied in computer science since the 1980s. You would think we've made some progress, right? So why is it that in 2022, we're still, cooking up new consensus protocols? Why don't we just pick one off the shelf and run with it? And I will argue that the answer to that is because for Ethereum, the protocol designers are going after a very, very ambitious wish list of properties. In fact, a wish list that up until recently, we did not know how to design protocols for. Okay, so three of the properties that I'll be talking about a bit more in detail is dynamic participation. So I've already mentioned this a little bit, that nodes can go to sleep, right? One way you can think of this is there might be unexpected temporary crash faults among nodes. And we want that the protocol continues to be live, even if nodes, even if a substantial fraction of the nodes can temporarily crash. We want some notion of accountability, which is that if nodes misbehave and they drive the system into, for example, a safety violation, that then we can slash malicious validators and we can take their state. We want a property called finality, which is that if the network can partition, we want to still have a property of safety. So we want to still ensure consistency, even if the network may partition. We want a property called reorg resilience, by which we mean that honest blocks cannot be reorged. Honest blocks cannot be removed from the longest chain. We want some notion of fast confirmation. So, just qualitatively speaking, transactions should be confirmed quickly, right? Not within like 1 hour in Bitcoin. And we want this protocol to be communication efficient. In particular, we would like to run this protocol at least among like 1 million validators, right? So the protocol needs to scale. And in the literature, we know 2 families of protocols. One are kind of from the Nakamoto family. And these protocols, they're protocols like longest chain. These protocols are very good at dynamic participation, and they're very communication efficient. But they're not very good at accountability, reorg resilience, finality, and fast confirmation. And on the other hand, there are PBFT style protocols, propose and vote style protocols, and they're almost the opposite. They're very good at finality, they're very good at fast confirmation, they're good at accountability and at reorg resilience, but they cannot handle dynamic participation, and they're not very communication efficient. So I see there's a question whether there's an assumption regarding access to a correct time server source by all the nodes. That is the case in Ethereum, yes. It's assumed that protocols know the time. Participants know the time. We will see this later. There's like a schedule of time slots, and if you don't know what time slot you're in, then you have a problem. So if we look at this wish list, right, we see that the color coding here is intentional, and you'll see this throughout the talk, that we have these orange protocols, right, that have these orange properties such as dynamic participation, and we have these blue protocols that have these blue properties such as accountability and finality. And in our wish list, the color coding here already hints to the fact that there is not one single protocol that kind of has all the properties that we would like to have. So in the first half of the talk, I'll be talking about a work called ebb-and-flow protocols, where it's all about bringing together dynamic participation and accountability and finality. And then later, I'll be talking about how to get reorg resilience, communication efficiency, and fast confirmation into the mix. So let's get started on the first half. So proof of work Ethereum, right, has this, it's an orange protocol, right? It's a Nakamoto style protocol. And it has this remarkable property, which we call availability. So let's see what that means. So we're running our blockchain, right? Here are our consensus participants. They are growing this blockchain on the left. And, they mine away. And, one day, half of the network disappears. And then what happens? Well, not much, right? The rest of the network, this is, at some point, difficulty adjustment will happen in proof of work, but basically the network just keeps running, right? And this is what I mean when I say availability and the dynamic participation, right? Even if participation fluctuates, the protocol should remain live. You can think of this as a strengthening of the liveness property. Liveness under a lot of crash zones. Why is this a good property to have? Well, in proof of work, it's kind of natural because mining rate, hash rate fluctuates anyway over time. But even in proof of stake, this is a good property to have because you can, think of this as a model for, power outages, or as a model of censorship, or as a model for any sort of like government intervention that would force validators to suddenly disappear and stop doing their job. Right? And then on the other hand, we have this other family of protocols, the PBFT style protocols, the blue protocols, right? And these protocols, they work quite differently. The way they work is like this. Somebody proposes a block, and then everybody takes a vote on this block. And if the block reaches a quorum, meaning it gets, typically more than 2/3 of the votes of the network, right? Then the block gets a special green status and kind of makes its way towards confirmation. And an interesting property of this is if you ever have a fork, right? You ever try to confirm two conflicting blocks, for example, right? Then in order to be confirmed, they need to have this green status. And in order to have this green status, they need to have 2/3 votes. But if the first block has 2/3 votes, right, then for the second block, there just isn't enough, there aren't enough votes left, right? There's only 1/3 votes left. So the only way the second block can also have the special green status, and you can see two conflicting confirmations, is if there are at least 1/3 of nodes that sign both blocks, that vote for both blocks. And that's a violation of the protocol. So what you can do then is you can look at these votes and you can be like, no. There are, a bunch of people here who have signed two things. They should not have been doing this. And I know exactly who they are. So what this gives me is a property we call accountable safety. It means that if there is two conflicting confirmations, basically a safety violation, we can identify 1/3 of the validator set must have provably violated the protocol. And you can think of this as a strengthening of the safety property, because the safety property says if the adversary is less than 1/3, for example, then there will not be a safety violation. And this property, accountable safety, says if there is a safety violation, then more than 1/3, or at least 1/3, have provably violated the protocol. This immediately implies that if the adversary is weaker than 1/3, since the honest guys don't violate the protocol, there cannot be a safety violation. The only way this statement can be true is if, in fact, there is no safety violation. And so from this, it becomes clear that accountable safety is a strengthening of the safety property. Now, the sad thing is these blue protocols, right, don't have this orange property, this availability property. And it's fairly easy to see, right? If somebody proposes a block, then half of the network goes offline. You just never get enough votes to get this block to the green status. And so you will never confirm stuff, and so your liveness is broken. So you don't have availability in these blue protocols. And on the other hand, these orange protocols, they do not have the accountable safety property. They don't have this blue property, right? And that's also not so difficult to see. If you just imagine, two like, K-deep conflicting chains, right, can be produced from entirely non-overlapping validator sets, right? But just because you have two conflicting confirmations doesn't mean that I can now point to somebody and say, hey, you have signed two blocks, or you have produced two blocks, you have voted for two things, right? So I cannot hold validators accountable for safety violation. So this begs a question, right? Both of these properties are good. Both of these properties are such that we would like to have them in the system. Why do we not know a protocol that has both of these properties? Can we have a protocol that has both of these properties? And the answer to this, no. We can actually prove that there cannot be a single ledger that has both availability and accountable safety property. So that's a bummer. What do we do, right? So what we were hoping for was a single ledger that is both available and accountably safe, but we know that that's impossible. So what can we do instead? So the proposal we have is, how about we decompose this ledger? So how about we decompose this ledger into an available full ledger and an accountably safe and final prefix ledger? Okay. Why is this useful? Well, before we have seen that protocols are either orange protocols or blue protocols. And this means that the protocol designer needs to make a choice for all the users, whether they will, at the end of the day, have to live with a blue protocol or an orange protocol. But now this approach gives us a way for the users to, to leave the decision up to the users, whether they want, to use the orange ledger or the blue ledger. And that may depend on their application. So the user can now choose. If the user sells cars, right, then going with slightly slower ledger that has the better safety properties, right, but might not be available, is okay, right, because safety is all that matters. It's important that transactions are not rolled back after the car has left the parking lot, right? Whereas if the user is selling coffee, it would probably follow the available full ledger because liveness matters, right? It's more important. It's unlikely that somebody would go through the hassle of partitioning the network only to do a double spend to steal a coffee, right? But what's important is that, coffee gets cold very quickly, so the coffee transaction needs to settle quickly, and so it's important that the ledger always be live. So users can now make a choice, and if you think about this idea of nesting ledgers, you will notice that you've seen this before, right? If you think back, for example, to Bitcoin, we've said earlier that there's this K-deep rule, right? And depending on how you choose your K, you see exactly this, right? For different Ks, you see different nested ledgers, right? If your K is small, you see a very long ledger. You favor liveness over safety. If you choose a large K, you see only a short prefix. So you favor you have lower confirmation error probability, but your ledger will be slower. Your transactions will confirm slower. So, you've seen this idea before, right? And it's the fact that, we are enforcing this nesting is what we call the ebb and flow property. And the reason we call it this is if we plot, the behavior of these two ledgers with respect to each other. Okay, so if we, over time, plot the ledger length, right, and we think of an environment where, maybe there's a network partition sometime in this gray shaded area here. The participation levels are fluctuating, right? So sometimes the participation is high; those are the green areas. Sometimes the participation is low; those are the white areas. Then our available full ledger, right, always keeps going, right? Its job is to maintain liveness. And it'll just always keep going. It will see a safety violation possibly under network partition. That's unavoidable. But in particular, it will also be live even if there's no participation. So this is kind of the optimistic ledger, right? It always assumes that if I don't hear from the other guys in the network, it's probably because they're crashed, because they're asleep. So it's safe for me to keep going. And that's wrong if there's a network partition, but that's right if the participation is low. And on the other hand, there's kind of the more conservative blue ledger, this accountable finalized prefix. And the accountable finalized prefix is kind of the pessimistic ledger, right? Every time it doesn't hear from other nodes in the network, it thinks, oh, no, they're probably partitioned off, they're doing something else. I better not take any more decisions. I better halt, right? And the result of that is that if participation is low, then this ledger stalls, right? Even though we would, want to keep going, right? Because it's just that they're crashed. But if the reason that we don't hear from these other nodes is because of a network partition, then this accountable finalized prefix, rightfully stalls, right? So this is all about, doing the right thing in the right situation. It's just that we cannot tell the two situations apart, and so we cannot come up with a protocol that always does the right thing. And so as a way to kind of trade this off, the idea here is to have two ledgers, and you can pick which of the two scenarios you want to be wrong or you want to be right. So it's important to realize up to this point, right? I've only told you what I want, right? I haven't given you any idea of how we get there and how we construct this thing. I've only given you a wish list. I've only tried to argue why this would make sense. If we had something like this, it would be extremely useful. So how do we actually build this? And the idea how to build this is kind of nice and reminds us of what we've seen earlier, right? So here's one way how we can build this. We take a longest chain protocol, right? In our big consensus protocol, right? Our big consensus protocol now has transactions coming in and two ledgers coming out, right? Okay, that's already good. I've explained to you why it makes sense to have these two ledgers. I've also mentioned to you that the blue ledger is always a prefix of the orange ledger. And in order to build a protocol with this ebb and flow property, here's something we can do. We first take the transactions and put them in our longest chain protocol. That's an orange protocol, right? That gives us this orange ledger here. This is the ledger we can output as an available ledger. Then we're going to take checkpoints from this orange ledger and put it into an accountably safe, partially synchronous BFD protocol. And the output of that protocol is this blue ledger, and this blue ledger is accountably safe and has finality. Right? The only thing So in the ebb and flow paper, we gave away how, there's like a prefixing operation we can do now, something we can do to the blue ledger and to this orange ledger to ensure the prefix property, right? Because up to this point, there's nothing makes sure that one ledger is a prefix of the other. So there's a way how we can do something with these two ledgers in order to ensure that there's always a prefix relation. The problem if we do this is, it's a bit deep in the woods perhaps, it's called lack of predictable transaction validity. What we mean by this is that after this prefix operation, basically, in the prefix operation, we take the blue ledger, prepend it to the orange ledger, and then go through and remove all duplicate transactions. And what this means is that as a node is building new blocks in the longest chain protocol, it doesn't know necessarily whether there will be any transactions prefixed to this orange ledger that might make some of the transactions that it's adding to the longest chain might make them invalid. And from a consensus perspective, that's not a problem because you just go through the ledger and remove any invalid transactions, and everybody will do the same because you have agreement on the ledger, and everything will be fine. But open up, for example, a spamming vector, right? An adversary could now spam the network with transactions that look valid but will turn out to be invalid. In particular, if the network is just recovering from a network partition and maybe not everybody sees the same blue ledger yet, and then some of the space in this orange ledger will be taken up by transactions that do not contribute to the actual useful throughput of the system. So in order to work around that, a standard approach is to say, okay, let's just take this blue ledger, right, these checkpoints, and make the longest chain protocol respect these checkpoints. Let's change the longest chain protocol to respect these checkpoints. Now we have this feedback loop. And there's a work that appeared in Financial Crypto where they show how to analyze this feedback loop. The problem with this protocol is that it doesn't give us accountable safety with the choice of protocol that they have for this box here, right? And the approach there is not as black box as we would like it to be. It's not clear how to put an accountably safe protocol there immediately. And so we took that analysis technique, and we were able to bring it into this kind of black boxy fashion and put an accountably safe partially synchronous BFT protocol here. And then this gives us the desired result. So we get a theorem at the end of this, which is that the prefix ledger, the blue one, is accountably secure under network partition with resilience of 33% of all participants. And the orange ledger, the full ledger, is secure under dynamic participation with resilience 50% of awake participants. And as we want for the ebb and flow property, these ledgers are consistent. So the finalized prefix is always a prefix, in fact, of the available full ledger. Just a side note that's interesting, perhaps, is the fact that each of these properties, the orange and the blue property, are kind of marginally optimal in the sense that if you took an ebb and flow protocol and you just forget about the orange ledger and look only at the blue ledger, you get a protocol that behaves pretty much in terms of the security guarantees like a PBFT style protocol. And if you forget about the blue ledger, you only look at the orange ledger, you get a protocol that behaves pretty much like a Nakamoto style protocol. So it's kind of interesting that to make the two ledgers prefixes of each other did not cost us anything in terms of resilience. There was no trade-off that we had to accept. Okay, cool. So this gives us some understanding of why the architecture looks the way it does, and it also gives us some understanding on how to analyze this feedback loop. Right? So we can now come to the second part of the talk, which is about LMD Ghost and the challenges around it. And remember, if we go back to our wish list, what this is about is coming up with a protocol that has this dynamic participation and communication efficiency of a longest chain protocol, but also adds reorg resilience and fast confirmation into the mix. So you've seen before, right? If I go back to this construction. In this construction, we haven't used LND Ghost in this box. We have used the longest chain protocol because we understand quite well how this protocol behaves. And we have a security proof for it. But in Ethereum's construction, there's the LND Ghost protocol here. Right. So the reason they're doing this is because the longest chain protocol does not have all the properties that they want of this first box. And in particular, in the longest chain would only have dynamic participation and communication efficiency. And what we would like to add to the mix is reorg resilience and fast confirmation. So the work I'm about to talk, I'll give you a kind of a brief explanation of LMD Ghost and some of the challenges with it, and then I'll talk about a new protocol called Goldfish, which we can kind of drop into this first box. So LMD Ghost. LMD Ghost, remember, we're now in the model that we're now concerned about, right? Is no longer accountability, no longer partition tolerance. That's all taken care of by this finality gadget and accountability gadget. What we're now interested in is a model with delta bounded delay, dynamic participation, honest majority. Okay, so that's the model we're in. And in this model, the LMD Ghost protocol, somewhat simplified, works like this, right? Time has time slots. So time is slotted into time slots, and every time slot consists of two phases. Okay. For every time slot, there is a block proposer. There are two roles of participants. One is block proposer, and the other one is voting committee members. Okay, and we assume there's some exogenous kind of randomness beacon that gives us one block proposer and a committee of voters for every time slot. Sorry. Then at the beginning of the time slot, it's the proposer's turn. The proposer runs what is called fork choice and then proposes a block. Fork choice means the following, right? It's what longest chain is in the longest chain protocol. It means you have your block tree of valid blocks. Now in this protocol, there's not just valid blocks, there are also some votes. So blocks, there are blocks, and on every block there can be some votes. And in this combination of blocks and votes, we're now running the fork choice rule, and it's the ghost fork choice rule, greedy heaviest observed subtree. That's a mouthful. What it really means is the following. You start at the genesis block, and you count for every direct child the number of votes in the subtree rooted at that child. So for example, this subtree has 6 votes. This subtree has 3 votes. And then you take a step into the subtree. You go to the child that has the most votes in its subtree. So in this case, the next block that we visit is this block tx1. And then we recurse. So we count the votes in this subtree. Those are 3. And we count the votes in that subtree. Those are 2. And we take a step into the subtree with the most votes. We do this until we reach a leaf. And then we have chosen our fork. Right now, this is this block, and together with its prefix, that is basically the fork that we have chosen. And the proposer then produces a new block, extending this leaf block. And then delta time later, so at the beginning of the next phase of this slot, right, the voters now also run fork choice, right? And hopefully, by this recursive structure of the fork choice rule, they should now arrive at the proposal that the proposer has just created. Right? And then they cast a vote. So they produce some of these new votes, and these votes hopefully then go to this proposal. That's the idea how the protocol should work. And then the protocol in the next time slot just repeats. So first thing to notice, right, there's no confirmation rule here. We have this fork choice mechanism, but there's no statement on what part of the chosen fork you should consider stable, right? There's no like k-deep, no like explicit like chop the last this and this many blocks off, and then you can be sure with this and this probability that your ledger will be safe. The other issue with this protocol is what we call swaying voters. And the idea here is as follows. If the proposer makes this proposal, right? So the proposer has just done its job. now it's the voters' turn. Then just before the voters take a vote, just before the vote deadline, right, an adversary can release a vote from the previous time slot, right, onto a competing block, right? Now these two, for the purposes of the fork choice rule, right, these two subtrees, once we're visiting TX1, these two subtrees, they're tied, right? Some nodes might see one of the subtrees as leading, some nodes might see the other subtree as leading, right? This means that, you know, the honest guys aren't consistent in what they vote for, right? Some of them might vote for TX4, some of them might vote for TX5. If we're unlucky, for example, more vote for TX4 than vote for TX5, and then this fresh proposal from our honest proposer is reorged out of the chain, right? Will not appear in the chosen fork in the canonical chain going forward. So this is what we call a reorg, and this is something that we would like to get rid of, and not just because, you know, of various like incentive issues that come with this, but also because this kind of an attack in this protocol can be you know, this technique can be extended to turn this into like a full-blown safety and liveness attack on the protocol. So this is what we do in the balancing attacks, and if you're curious, you can check out some of the references where we describe these attacks both in the reorg setting as well as on safety and liveness of the protocol. So in order to solve this, what we're proposing in this most recent preprint is the Goldfish protocol. You'll see in a moment why it's called Goldfish. It's because it's a rather forgetful protocol. In Goldfish, time is still slotted, so there are still time slots, but every time slot now consists of 3 phases. Okay? First phase is a proposal phase. Second phase is a voting phase, just like in LMD Ghost. And the third phase is a confirmation phase. That was the thing, one of the things that was missing in LMD Ghost. For every slot, we still assume that there is some proposer, L sub T, and we assume there is some voting committee. And these are, again, you know, this is how we abstract the lottery, right? We assume that these come kind of from outside the protocol. They're given to us. And every validator now has a particular view about the protocol, right? And in its view, there are 2 kind of data structures. One is this set of blocks and votes. We call it VI. And one is a buffer. And what's important about the buffer is whenever a validator receives a message from the network, unlike in many other protocols, it does not immediately take this message into kind of its you know, block tree structure, right? Instead, all messages that arrive at the validator, they first get buffered, and then they get admitted from the buffer into this block tree with the votes into VI only at carefully chosen points in time. That's a key ingredient of the protocol. In particular, bear with me, this looks a little mathy and overloading, but the intuition is actually quite simple. I'll walk you through this. At the beginning of the proposal phase, right, the proposer takes its buffer and adds whatever it has in its buffer into its V. Then it, you know, runs this ghost rule, right? It produces a new block. It extends this with a new block, and it adds this new block to its V as well. And then it broadcasts basically its V. It sends out whatever it has in V. Then comes the vote phase. At the beginning of the vote phase, every voter goes through their buffer, and they look in their buffer for a proposal from the legitimate proposer of the current time slot. Okay, so whatever the proposal was sent here, hopefully will get fished out in this step at the voter. And then whatever was the proposal, that's what they also add into their V. Then they run the ghost rule again, just as before. They identify a certain tip, B target, and then they broadcast a vote on that target. And then finally, in the confirmation step, the confirmation phase, everybody takes whatever they have in their buffer, they add it to their V, they run this ghost rule, and then they identify a canonical chain, and they chop off all the blocks at the end that are younger than a certain amount of time tconf. So everything that was produced, let's say, in the last 10 minutes or something like this, right? We're not going to confirm those yet, but everything that is in the canonical chain and is older than 10 minutes ago, that we consider is probably going to stick around forever. And I hope to convince you that this is actually secure. Okay, so there's two key ingredients here. One is what we call vote buffering. So the buffering is what happens at the first steps here, right? The second, this is a technique that we've seen for the first time in a preprint of something called the highway paper. I don't think this has been published, but it's on archive since last year summer or something, and it uses this technique, and it turns out this technique is quite useful. And the second thing is a technique that is also critical, not just to make vote buffering feasible, but also critical in the security of this protocol, is what we call vote expiry. So whenever we run this ghost rule, we're not running it based on all votes. We're only running it based on votes from the most recent voting phase, right? So that means during the first two phases, we run it based on votes from t-1, and in the confirmation phase, we run it based on votes from the current time slot. And then finally, I've given you a confirmation rule, right? So that's good. So now I want to convince you of 3 steps. Okay, 3 steps I need to show you reorg resilience. So reorg resilience is that when an honest proposer makes a proposal, this proposal should actually make it to the output ledger. That is what I want to show first in 3 steps. And then from reorg resilience, it turns out it's relatively easy to show safety and liveness of this protocol. So for reorg resilience, the first property I want to convince you of is that if the proposer in a certain time slot is honest, then all slot T honest voters vote for its proposal in this slot, right? Why is that the case? Okay, suppose we're here, we're just before the confirmation phase of the previous time slot, right? Now, we look at kind of the a toy example of like the view on the protocol, right? This is the scenario that we need to kind of take care of is the swaying scenario that we've seen earlier, right? This kind of disagreement about what is the right block to vote for, right? So, we can look at the view of like 3 nodes, right, on the network, 3 honest nodes. And suppose that, just after the confirmation time, the confirmation phase of the previous time slot, some honest node has seen some sway votes showing up, right? These 2 votes here. The only way that, at this point in time, this honest node, you guys see my pointer, right? My mouse?
Yes, yes.
Okay, cool. Lucky. Otherwise, this would be hard. So the only way in which some honest node in its V, right, can have these sway votes just after the confirmation phase of the previous time slot is if it had actually received them just before the confirmation phase, right? But since the confirmation phase, so now they have inconsistent view. They have inconsistent fork choice, right? If they were to run this fork choice rule, they would see inconsistent blocks as leading. But note that the last time anybody has updated this V, right? Now they're not updating the V anymore, right? Everything that happens after this confirmation phase of time slot t-1 will only enter their buffer, right? So there are no updates on their Vs up until the next voting phase of time slot t. So if an honest guy has these sway votes in its V by the confirmation phase of the previous time slot, then since this phase is delta time long, these sway votes will also have propagated to the proposer of the current time slot t. Okay, so everybody has now in their buffer, every honest guy now has in their buffer these sway votes, but they're not yet in V, right? They're only in their buffer. But suppose the guy in the middle is the proposer in time slot t, right? Then what it does, because of this line in the protocol, is that it takes these sway votes from its buffer and adds it to its V, right? Now it makes its proposal. The proposal will now extend this block, right? and it sends out its view of the protocol, right? Its V, its its proposal with the new block and all these votes. And then every honest voter, right, gets the V of the proposer, and also adds these sway votes and this new block to its V, right? Now everybody has a consistent view of what the fork choice should be, right? And everybody will be voting on the same block. So this is what vote buffering gives us, right? Vote buffering makes it such that the V of an honest proposer is a superset of all the Vs of all other honest guys. And so when they fish out the proposal in the voting phase and they add it to their Vs, they all end up in the same with the same V. That's what vote buffering gives us. So I hope to have convinced you that if the proposer in the slot is honest, then all honest voters in that slot will vote for the proposal. The second thing I want to convince you of is that if in slot T-1, all honest voters vote into some subtree rooted at B, then the same will be true in slot T. All honest voters in slot T will also vote into the subtree rooted at B. Why is that true? In order to understand this, we have to look into the voting instructions, right? And we assume, for contradiction, it was not the case, right? So there was some honest guy who voted not into B, not into the subtree rooted at B, but into some other subtree, into this blue subtree. Now, why is that not possible? Well, remember we have this vote expiry property, right? So in time slot T, all we're considering are votes from time slot T-1. But by assumption, in time slot T-1, all honest guys have voted into B, right? So the only nodes that can have voted into this blue subtree, into this conflicting subtree, are adversarial. But the honest guys are the majority, right? So there are more votes in the subtree rooted at B than in the subtree, in this blue subtree. So it's not possible that by the structure of the ghost rule, it's not possible that an honest guy ends up voting in the blue block, in the blue subtree. So as a result, in slot T, all honest voters indeed vote into the subtree rooted at B, as we like. Okay, cool. So I think you see by now, right? We start with this property that if an honest proposer makes a proposal, then in slot T, everybody will vote for it. And then we can do this induction step, right? And we reach the conclusion that throughout time, all honest guys will always be voting for this proposal, assuming that the committees are always honest majority. And the result of this is that if there is an honest proposal, if a block gets proposed by an honest proposer, then this block will enter the ledger, and it will do so with a prefix that is determined at the time of the proposal. And then it's relatively straightforward to see from here why Goldfish is safe and live, because honest proposers happen every now and then, right? Quite frequently, in fact, because the honest guys are even in the majority. And so as long as you make sure that you choose the confirmation time so long that you can be virtually certain that there will be some honest proposer in there, right? You can trust that the honest proposer will, on the one hand, rope in any unconfirmed transactions. So that's what gives you liveness. And on the other hand, it will stabilize the prefix that it's building on. And so everything that's in that prefix cannot be unconfirmed. And that gives you safety. So, I've hopefully convinced you that Goldfish is quite simple, a protocol intentionally similar to LNB Ghost. From reorg resilience, which it has, we can bootstrap security quite easily. It supports dynamic participation. I haven't talked about this specifically here, but you can find it all in the preprint. It supports subsampling of voter committees, and as a result, the communication efficiency is good. We show that it's composable with finality and accountability gadgets, and there's an extension that we also describe in the preprint on how to get fast confirmation under optimistic conditions. Optimistic meaning the adversary is no stronger than 25%. A challenge with this protocol is that because of vote expiry is what makes the protocol forgetful. That's what got it the name Goldfish. This protocol is a bit more vulnerable if there are periods of asynchrony, right? If votes don't make it to all other participants, then because we only consider the most recent votes, nodes might deconfirm stuff. Okay, so let me wrap up. In the first half, I've shown you with ebb and flow protocols how we can combine dynamic participation, accountability, and finality. In the second part, I've shown you with Goldfish how we can get reorg resilience, fast confirmation, and communication efficiency into the mix. I hope to have given you some taste on blockchain-inspired consensus problems with this ebb and flow approach that we can use to circumvent some of the impossibility results in the space. With Goldfish, a simple and provably secure drop-in replacement construction for LMD Ghost. And yeah, our overall aim here is to see if we can work together to strengthen Ethereum security. Thank you.
Yeah, thanks a lot, Yong-Him, for your great presentation. And because of the time, maybe I just have like 2 quick questions. So first, right, if we go back to your previous slides, we have like 6 goals, right, in the wish list. So perhaps, right, another approach is to start from BFT, right, and then like to support dynamic participation as right what Linren and his collaborators are doing. And could you please quickly comment maybe on that approach?
I think what you're pointing out. So there's a very recent paper by Linren and collaborators. I think they're very much interested in dynamic participation together with fast confirmation. Mm-hmm. I think they also get reorg resilience. I don't think they get accountability and finality. That seems kind of inherent. So this approach of having the gadgets with like blue protocols and orange protocols, I think we'll still need. But it's true. We have a protocol now that is that basically has dynamic participation and fast confirmation and has a little bit more of this PBFT flavor to it than longest chain.
Oh, cool. Yeah, very clear. And another quick question, right? You mentioned that it might have some, it might be vulnerable, right, to some maybe network level attacks, right? Asynchrony. It seems to me maybe before the latest checkpoint, you are still okay, right? Only affect the partial, maybe after the latest checkpoint. Yes. Am I right? Okay, cool.
Yes. Yeah, that's correct. I think the answer to this is, in some sense, this vulnerability under asynchrony is not a design goal of this protocol, right? Mm-hmm. This protocol is designed for a synchronous network with dynamic participation, and it's the job of the finality and the accountability gadgets to basically, take care of the asynchrony and to give us accountable safety. Yeah.
Nice. Yeah, thanks again. Any other questions from our audience? Yeah, if not, let's thank our speaker, Yong-Him.
Thank you guys for having me. Yes,
for joining
us.
This
is great.
Yeah.
Thank you.
Hey, yeah, bye-bye.
Bye.